Hello, everyone. I'm Daniel, and I'm going to talk about fast and robust quantum state tomography from few basis measurements. This is joint work with Fernando Brandao from Caltech and AWS and Richard Kueng from the Johannes Kepler University Linz. And you can find a work with the same title on the archive, where you also find more details on what I'm going to tell you about now. So this is a talk about tomography of states of low rank. So the setting of this problem is as follows. We assume we're given access to copies of some state rho, which we don't know, and it lives in some dimension D, and we're given the promise that the rank R is very small compared to the dimension D. And then we are allowed to perform measurements on individual copies of rho. So in particular, what we're not allowed to do is take many copies of rho, store them in quantum memory, and then measure them collectively. We're only allowed to take one copy, then maybe apply some unitary to this state and gather measurement statistics whenever we measure in a given basis. And our goal from this is from the measurement statistics in different bases we're going to measure to actually obtain a classical description of the state, rho, that is close, epsilon close in trace distance to our target state. So this is the setup of the problem. And there are many relevant resources to optimize for when trying to work with this problem. Namely, the first of all is the sample complexity. So how many copies of the state rho do we actually need to produce to obtain a good approximation to it? But it is also important to optimize the number of measurement settings because in many platforms, it actually takes a lot of time and calibration to measure different bases corresponding to different unitaries. So it is important that we also minimize the number of different unitaries we actually need to measure. We also want that the classical post-processing, that is after we gather the data, how do we actually obtain the classical description, that this is as efficient as possible. And on top of that, we also want that the memory we require to perform this task is as little as possible as well. On top of that, there are also some qualitative aspects that every good tomography algorithm should have. First, it should be robust, and then it should only be robust to statistical noise, because we of course never will get perfect measurement statistics. There will always be some statistical fluctuations, but also to imperfections in both the preparation of the states and the measurements, because these will also never be perfect and noiseless. On top of that, it is desirable, although I would say this is not a strict requirement, that you can implement the algorithm online. That is, while you're still gathering data from your experiments, you can already start the reconstruction process in parallel, so that the whole process is actually more efficient and takes less time. And in addition, it is very important that the measurements underlying the algorithm are as simple as possible, because we don't want to have to implement, say, exponentially deep quantum circuits or experimentally infeasible measurements. We want the protocol to be as experimentally friendly as possible. Good. Now that we discussed the relevant resources, let us quickly summarize what is the state of the art regarding this problem and how we improve upon it. So low-rank tomography has been studied a lot in the literature. So for instance, there's the compressed sensing approach, which corresponds to the CS in the table. There's also the projected least square approach to this problem. And there are also quite tight lower bounds known for the problem. In particular, it is known by work by Wolf and others that the number of basis settings has to scale with R, so the number of different bases we need to measure. Also, the number of state copies is known to scale linearly with dimension and quadratically with the rank. This is work by Arrow and Ha. And well, from this, we infer a trivial lower bound on what is the time for the post-processing, namely the same, because we also have to load in the data to actually perform the post-processing. And we also have a trivial lower bound on the memory required to do this task, because at some point we have to write down our state, right? And if it's a state in a d-dimensional space of rank R, we need at least d times R many parameters to write it down. So this is the memory. And you see that different approaches perform quite well in some of these for some of these parameters. So for instance, computer sensing excels in the basis settings, but the runtime is not great, and the exact number of state copies is unknown, whereas other approaches like projected least squares achieve optimal number of state copies, but in general need many basis settings. So, and in particular, none of these approaches simultaneously saturates the lower bounds. And our algorithm actually, if we forget about the scaling and the error, is the first to simultaneously obtain the best possible number of basis settings and also state copies. And in addition to that, it also improves upon the runtime required. So it's the first one to actually reach quadratic runtime. And it also matches the lower bound in memory, where it also improves upon the other algorithms in the literature significantly. Again, at the cost of a worse dependency on the error. I should say that our algorithm also fulfills the qualitative improvements or desiderata I mentioned before, such as being robust, provably robust against imperfections in both the preparation and measurements, and also statistical noise, something which is more difficult to establish for the other methods I mentioned before. And we have, again, also the fact that it can be implemented online. On top of that, our algorithm can also be implemented on a quantum computer, which would get a speed up to actually obtain a classical description of the quantum state. So implementing our algorithm on a quantum computer would lead to a scaling of the runtime that is actually d to the 1.5 instead of d squared. So quantum speed up for that task. And I must say that all of these results I'm showing you here are suppressing polylog dependencies and all hold with a constant probability of success. So that's all, these are all things I'm suppressing. Okay, so we see that our algorithm has many desirable features and has a pretty good performance in almost all of the parameters of this problem. But let us now discuss how we actually achieve that. So these other problems, these other algorithms I mentioned before, they solve a linear inversion problem, whereas our algorithm is an iterative algorithm. The iteration rule, the update rule is based on mirror descent with the von Neumann entropy as a potential, if that says something to you. And this is essentially the same workhorse behind previous SOL STP quantum speedups. And I must say that a previous update rule has also appeared also in the tomography literature in the work by Yusri. And the whole way our algorithm works is similar in spirit to the self-guided tomography scheme by Ferry. So how does the algorithm actually work? At every step of every iteration, we're going to have a guess for what our target state rho is, and this guess will be signal. Then at each time step, we'll try to distinguish our guess, our current guess, from the actual state. And this, I mean, in the one-shot regime, right? How do we distinguish through quantum states? Well, we get some bounded observable P, such that the expectation value of rho and sigma under P differs by at least epsilon. That's what it means to have a way of distinguishing up to epsilon to quantum states. And then we're going to use this information that we're able to distinguish the target state from our current guess to actually improve our guess for what the state actually is. More precisely, we can show that if we have this information that this observable P can be used to distinguish rho from our guess, let's say at iteration T, and our guess has this Gibbs state form, then we can actually update this Hamiltonian of our guess in the direction of P, so add some sort of energy penalty in that direction. And if we update our guess in this way, we actually become closer in relative entropy. So if we denote by S, the relative entropy between the target state and our guess, we see that by updating this way, we actually get closer by epsilon squared. So every time we are able to distinguish, we become closer in the relative entropy, which can be thought as some sort of distance measure between the states to our target. Okay, so that's the philosophy of the algorithm. And now we see that we need somehow a way of distinguishing two states, our guess and the actual state, right? And what we're going to do for that are random measurements. So it follows from results of Matthews and others that if we actually take an approximate for design and measure two states in the basis defined by that unitary, then the total variation distance between the two underlying probability distributions of the outcomes is proportional to the Hilbert-Schmidt distance between the two states. And this happens with constant probability. So how can we actually use this to obtain ways to distinguish two quantum states? Well, we measure some random for design, and we compare the measurement statistics with respect to this basis for rho and sigma. If the histograms are close, that is, this total variation is small, then they are indistinguishable in this basis. And from this statement, we know that they're likely close in Hilbert-Schmidt distance. However, if this total variation distance of the histograms in this basis is large, then they are distinguishable in this basis, and we can actually make progress with the update rule I described before. So just to illustrate a bit how this algorithm works, usually we start at we take as our initial guess the maximally mixed state. We'll see in a second why this is a good idea, but it can be thought as some sort of maximum entropy principle. And then, for instance, if our target state is this state here on the boundary of this Bloch sphere, here we have a 1-qubit example, then we could, for instance, start by measuring in the plus minus basis. And then for the maximally mixed state, the histogram will look approximately 50-50, right? Whereas for this state, it looks like this. So we see that these states are distinguishable by measuring in this basis. And then we can move on and propose an updated guess, which will be the sigma 1. And then we could, for instance, measure in the computational basis. If we then looked at the histogram of like our current guess and the target state, we see that they're pretty much distinguishable still. And then we use this information to update the Hamiltonian in the direction of 1. And then we're going to end up here where we can again measure some other bases and get closer and closer until the histograms start to look pretty similar for both our current guess of the state and the target. So that's morally how the algorithm works. Now, more precisely, the algorithm follows the following flowchart. As I mentioned before, we start with the maximally mixed state, and then we measure some random basis. If the histograms of the statistics of our guess and the state are distinguishable, look different, then we can just update the guess with the rule I mentioned before. However, if they're indistinguishable, then it means that with some probability, the Hilbert-Schmidt distance of the two states was small. However, it could be the case that we were just unlucky and that particular basis didn't lead to a good way of distinguishing the two states, even though they are still quite distinguishable. So what we do is we measure a couple more bases, compare the histograms, and if they're all similar, then and in the sense that they're all indistinguishable, then we suppress the probability of us making a mistake or getting a false positive, and then we are done. If we find one in which they are again distinguishable, well, we can update the guess again, and we go back to this step. So this is roughly how the algorithm works. And of course, one reasonable question at this point is, are we sure that we're going to end up at this place at some point? And how often does that happen? Well, let's analyze the convergence. As I mentioned before, we picked the maximally mixed state as the initial state. So the initial relative entropy between the target state and our initial guess is at most log of the dimension. And recall that the every time we find a way of distinguishing our target state and the guess, we decrease the relative entropy by a factor of epsilon squared. So as the relative entropy is always positive, this shows that the number of iterations we need to perform is at most log d epsilon to the minus 2, because then the relative entropy is essentially 0. And well, what happens if we don't need this many iterations? As I mentioned before, if we actually converge before reaching this many iterations, then it's very likely that the Hilbert-Schmidt distance between the target and the guess is small. And I mentioned at the beginning of the talk that we're actually interested not in obtaining a good Hilbert-Schmidt recovery, but actually a trace distance. And so, and I mentioned low rank, at no point so far the rank played any part, but here is where it actually plays a role. If we want to convert a promise, a bound in Hilbert-Schmidt distance to one in trace distance, we actually play square root of the rank factor while doing that. So that's where the rank assumption comes in, by converting this Hilbert-Schmidt distance into a trace distance bound. Now, what is the number of measurement settings that we need? Well, for each iteration, we need a constant number of measurement settings. So if we are distinguished, if we do not fail to distinguish, and we only need one, right? And then we can update. However, if we fail to distinguish first, we need to repeat this a constant number of times before we decide that the states are closed. In any case, we need a constant number of bases per iteration. So the number of basis settings is given by the number of iterations. And the number of samples we need for each iteration is d over epsilon to the minus 2, because this is the number of copies we need to recover the histograms of the measurements for that basis. So this completes the analysis of how we actually obtain the sample complexity for our algorithm and the number of basis settings. But you could also ask yourself, well, what about other measurement setups? Because right now I only talked about approximate 4 designs, and they can be implemented efficiently with a relatively short depth random unitary circuit, but this might still be out of reach for some experimental setups. And the nice thing about our approach is that all it requires is for generalizing what we just did from unitary 4 design to any measurement setup is an analog of this equation, which allows us to say how well we can distinguish states with this measurement setting. And for instance, we are then able to easily generalize our results to Clifford measurements, random Clifford measurements, which to the best of my knowledge was still an open problem. Because we showed that, or rather we import results of the literature to show that for random Clifford measurements, which are a 3 design but not a 4 design, essentially the same inequality holds, but you also have to pay some rank factors over here. And then we can play the same game and also obtain bounds on how many measurement settings and state copies you need to perform tomography with Clifford measurements. And we can also do k-local measurements, although in this setting, our results are not competitive. So whenever you're not measuring global unitaries, but only acting unitaries acting on k qubits, then we obtain this version of the inequality. And this constant comes from work by Lancian and Vinta, this square root of 18. And in order to make our result competitive also for more local settings, we need to improve this constant, which although it is hardly non-trivial, it is also likely to be suboptimal. So in some sense, we cannot at least prove that our technique outperforms other known techniques with more local measurement setups. However, it's still nice that we can see this trade-off between the locality and how difficult it is to actually perform tomography. And it would also be interesting to identify some classes of states for which this distinguishable. So what could be assumptions on the state rho such that we can also improve on how difficult it is to perform this distinguishability task and obtain better tomography bounds. Okay, so how do we actually now obtain also improvements for the post-processing? Because so far we only discussed sample complexity and measurement settings. So all the Gibbs states we iterate over have the following structure. So they can be written as a sum of some Hermitian matrices for which we know how to diagonalize them. So they are all of the form UI, DI, UI dagger, where the UIs are the known local quantum circuits we actually use to implement that measurement setting. And this DI encodes the information of how we actually distinguished that point from our previous guess. So we see that all the all the states we iterate over have highly structured Hamiltonian. And this can be used to obtain the more efficient post-processing. So because all we need at each iteration is to compare histograms, but as I mentioned, our algorithm is extremely robust, so you can actually approximately compute the measurement statistics and still get away with it. The algorithm still works. And then instead of actually diagonalizing the state to compute this Gibbs state, you can actually just perform a Taylor expansion, which as we only need a good approximation. And on top of that, you can use the fact that all the matrices involved are very sparse to do this Taylor approximation very fast, in the sense that instead of doing full, like dense vector matrix multiplication, you can actually just do sparse vector matrix multiplication, which gives us the d squared scaling in the post-processing instead of the d cubed if you had actually dense matrices involved. Okay, how do we also obtain speedups for the memory? Well, what are the things we actually need to store to run our algorithm? We only need to store the matrices here in the exponent. And if you are only local quantum circuits, you can also store them efficiently. And on top of that, these are diagonal matrices, so you also can store them efficiently. So the only for every iteration, we need to store order D parameters. And as the number of iterations is related to the rank of the state, we can actually only, you only need to store R times D many parameters, again, suppressing the dependency on the error. And the nice way is that, and the nice thing is that we actually find a way of doing all the steps of the algorithms without ever have to write down a dense matrix. So you can run the whole algorithm only requiring memory D times R. And as far as I know, this is the first algorithm to achieve this rigorously. Now, one possible critique of our algorithm is that it actually outputs this Hamiltonian such that if you exponentiate it and divide by the partition function, you obtain the state, whereas other algorithms actually output the full density matrix, or let's say a list of eigenvectors and eigenvalues for the state. And someone could interject that this is not a fair comparison, right? That, you know, the two forms of the output are not the same. So in order to address this, we also provide a way of efficiently diagonalizing the underlying Gibbs state and then obtaining a list of eigenvectors and eigenvalues for the Gibbs state. And this all without sacrificing the speedups I mentioned before. So this procedure of getting this Gibbs state and then transforming it into a list of eigenvalues and eigenvectors can all be done with the same memory scaling and runtime scaling. And it's based on the observation that if you have a Gibbs state, then it's quite easy to compute what is its square root. You just take the Hamiltonian and write 1/2 in front of it. And then there are randomized singular value decomposition algorithms, such as the one by Musco, that we can then use. these randomized SVD algorithms, they are so-called Bloch-Krylov methods, which means that they just work by repeatedly multiplying a matrix, some vectors with a matrix. And as mentioned before, as we have this highly sparse structure, we can do vector matrix multiplication more efficiently. And we are also under this low rank assumption, which is also needed for these SVD methods. So the important thing is that we can actually do a obtain the list of eigenvalues and eigenvectors using these randomized SVD methods from our Gibbs state, if you're interested in this form of output without losing the advantages as shown before. And last but not least, I would like to mention that the algorithm is also practical. So in particular, we saw in the first table that we beat all other proposals except for the scaling and accuracy. However, the scaling and accuracy is not really seen when we implemented this algorithm, in the sense that the number of basis measurements and so on didn't seem to scale too badly with the accuracy. And this is essentially because what happens when you implement the algorithm is that you observe that you can actually recycle information quite often. That is, once you updated the guess, you can then compute the measurement statistics for this new guess and compare it to the actual state. And it is very often the case that this measurement statistics can still be used to update the guess again, again, and again. So here in this plot, we, for instance, compared the performance of the algorithm against compressed sensing by taking 15 random bases. Here we see the number of qubits increasing. We also added some noise. And we see that, and this is a very pedestrian implementation of the algorithm, I would say. This is not the full-fledged version with all the bells and whistles. And we were still able to easily go to system sizes for which doing the recovery with compressed sensing methods is already quite difficult with just standard desktop computer. And the precision we achieved is still rather good, even though we only used 15 basis measurements to obtain rather large precision. I mean, of course, sorry, much larger precision that our theoretical bounds actually predict. So one of the open questions of this work is also showing rigorously that this worst case error dependency doesn't actually, that it's just too pessimistic, that this 1 over epsilon 2 scaling of the number of basis measurements or the extra one copies of the state is actually not tight. And with that, I would like to thank you for your attention, and we'll be happy to take questions during the conference.